This is the companion video to our ignition primary waveform video, primary voltage waveform. Now we're going to look at the primary ignition current pattern. Now for this video, like the last one, the first thing we're going to do is we're going to go out on the car. We're going to take a look at how the hookup is done to look at ignition primary current or amperage. And then once we've got an idea of how the setup is going to go, we're going to come back in here. We're going to talk through our waveform. And in this video, after we've gotten through this waveform, then we're going to go and take a little look at some real life examples. And I'll line them up and we'll look at the current and our voltage together in the same picture. And so you can kind of get what the correlation between the two looks like. So let's go ahead and head on out and take a look at the car, and then we'll come back and walk through this waveform. Okay, we're back on the car, and we're going to add another layer here. In the primary video, we went over the hookup of where to put all the wires if we wanted to test both primary and, in that video, secondary ignition voltage. So we still have that hookup set up and ready to go, but we're going to add one more layer in here. We're going to look at primary coil amperage as well, or primary circuit amperage. And we're going to do that by using a low amp current probe, an inductive probe. So we're just going to clamp this around one of the wires going to the coil. Now, nice part about it, our coil is a series circuit. From the switch through the coil to power, it's all a series circuit, which means I can connect on the power or ground side wherever it's easiest and get the same image. And because I'm connecting to the main power or ground to the coil, it's also going to give me the patterns for every firing event on the engine. So we'll take this, can come underneath. This is my positive side of the coil. I have one wire that's going to the choke, don't need that one. One wire that's coming over here to power up electronics and distributor, that's clearly not it. So this yellow wire here has to be my supply. Gonna make sure I put my probe on properly. It's turned on, set to the 20 amp mode. Most ignition systems are going to draw between about 3 and 10 amps, so the 20 amp mode is the one I want on my inductive current probe to make sure I get my best resolution on this image. Okay, so now we'll take a few patterns and we'll go ahead and look those over. Now we're back. Take a look through this particular waveform and see all that there is to see on the current waveform for our ignition primary. Now my scale in this is 0 amps to 3 to 10 amps. Somewhere in there. Depends on the coil design. That's why we have it depends. Depends on your coil design. So we have a variable scale over here. Much like our other waveform, we start at 0 amps. We need to end at 0 amps. So in this case, again, 0 amps because we're talking amperage, not voltage. We should start from 0. We got 0 amps, we got 0 amps. As soon as the switch closes, whether it's a set of contacts or a transistor, when that switch closes, it allows the current to start flowing. That's the point at which our primary voltage went to ground. Current starts to flow. As it does, we'll often see a little bit of what we term ringing or oscillation in the very beginning of that pattern. Don't stress if it's not there. If you test 6 coils on a V6 and 5 of them have good ringing here and 1 doesn't, well, look into why the 1 doesn't. So don't get too hung up on this, but we may get a little ringing, and then we have our ramp up. Because we're dealing with a coil of wire, when we start to flow energy or power into it, it starts to develop that magnetic field. Then we get some counter-electromotive force. The building of that magnetic field electrically opposes itself. That's why instead of going straight up, our voltage ramps up pretty gently typically. So our switch is closed here. That's the beginning of our dwell period. We're going to ramp up to our maximum current saturation, at which point it will either hold at that until it's ready to fire, which it did for a short period here, or we'll go ahead and open the switch, at which point we drop instantly to 0 amps of current flow. That ends our dwell period, and we're pretty much done with this at that point in time. Just like our primary voltage, from when the switch was closed till the switch opened, or the on period, we also call the dwell period. So once again, we'll line those up together when we look at some live examples. Now this particular one, this is what we deem a saturated driver. On the primary voltage, I showed you what current limiting looks like. This one has no current limiting. The current is just limited by the natural circuit itself. It will come up and it will hit a natural flow. It really has right in this area. It started to level out. If we would have left this on, it would have just kept going at about that same level. So we call this a saturated driver. If we had a current limited driver, then this would come up and it would have a very distinct flat top. It wouldn't have this little bit of a curve to it. It'd come up, flatten right out. But that's not the style we're looking at right here. What we're looking at is a saturated driver. So those are the two kinds of coil drivers we have. And again, whether it is a current limited or saturated driver, that all depends on the circuitry running it, not necessarily the coil itself. You will find, however, that a saturated driver coil is generally a higher resistance coil than a current limited coil is. So typically, once again, like a lot of things in this business, not always, because it depends. All right, so with that, we're going to go ahead and go pop up some waveforms and take a look and see what some waveforms on the Pico look like with our primary voltage and current put together. So our first waveform is a very standard saturated coil, pretty typical waveform. You'll see down here we have our switch turning on. At that particular point, we are about 12.5 volts. Next, we're going to switch to switch turning off. Then, of course, we have in between the two, that would be our dwell period from here to here. Next up, we have our firing line. That maxes out about 350 volts. That peak right up there. The next piece we have in here is going to be our spark line, or this section right here. That particular spark line is 1.8 milliseconds in duration. Hopefully you'll remember that our rule of thumb was roughly 1 to 2 milliseconds. And then at the end of this, we have a handful of coil oscillations. After that, we return to our source voltage, which is right again, back to about our 12.5, right down in here, before it turns on and starts to process all over again. Let's add in our current waveform real quick. First off, we're going to drop the scale on this to make this a little bit smaller. Minimize the size on that waveform. Slide it down and out of the way just a little bit. So next, we're going to look at views. Channels. Right now I only have channel A turned on. B, C, and D are off, but I have data on all of them. Here's channel B. That's the channel we're recording the current waveform on, or our amperage. The same spot, we have our beginning of dwell. We have our nice current ramp going right up here. We have the end of the dwell period where the switch opens up again, and we go right back to 0 amps. Everything looks nice and normal for a saturated type coil right here. Nothing too out of the ordinary. If you notice also, I'll draw a line at the beginning of dwell and at the end of dwell. And you'll notice the dwell period, the time our voltage is pulled low, is the exact same time our amperage is flowing. It's almost like the rules of electricity actually work. Pretty cool, huh? Now I'm going to add another piece in here. We're just going to go ahead and pull up and come back to views. I'm going to turn both of these channels off, and I'm going to bring up our ignition secondary. Now here we're just bebopping along, nothing special. Let's go ahead and bring this back to a full scale.
So here's our ignition. We're moving along. We are looking at, right around 5,000 volts. Now, I'm going to scroll forward because at the end of this capture, I went ahead and did a maximum test to see what the maximum coil output was going to be on this particular vehicle. So now I'm unzoomed. I pulled the coil wire out of the top of the distributor cap to maximize my coil output so I could see what that coil was truly capable of putting out. That's what this is over here. Looks like this was about my maximum. So what this is going to represent is the maximum available coil voltage. Again, with the engine running, I used a pair of plug wire pliers and I pulled the coil wire off the distributor cap, forcing it to open circuit temporarily, and that maxed it out. So it's going to show me exactly what our maximum available voltage is coming out of that coil. And in this case, that would be our peak up here. That's my number 2 cursor. So that's going to be 42.62 thousand volts. That coil can produce just about 43,000 volts. This one's not too shabby. Let's take a look at the next pattern. For our second primary waveform, now we're looking at an actual waveform off of a current limited circuit ignition coil. So I'm going to start by bringing down this measuring line. Let's see, our starting voltage was 14.78 volts. We started and finished at the same voltage. That's good. We come down to about ground. It was about 1 volt. That's acceptable. So you'll notice right where our current limiting started, right there. Right, we didn't turn the switch didn't open yet. We haven't turned the circuit off. It's still operating. But there we stepped up in voltage. We didn't go back to the same as source voltage. But we're also still not holding to ground. So what we're doing now is maintaining the same current, or roughly the same current flow in the circuit. So let's measure that. So I'm going to bring this cursor up. And you'll see we're right about 10 volts. So we were around 14 or so up here. Actually, I think we're a little higher than that. Let's double check. Get that cursor right up there. So we're about 14 and a half, 14.8 there. Right here, we're just about 10 volts dead even. So we were still feeding about 4.8 volts to that coil to maintain our charge or keep that magnetic field stable. Everything else in the pattern looks the same. Let's measure our peak real quick here. Looks like we max out at about 328 volts in the primary. That's not too shabby. Quick measurement of our spark line. Gives us roughly 1.5 milliseconds. That's our number in the box at the top. Right there. That's our delta. This is cursor 1. This is cursor 2. The time between them is 1.438 milliseconds, or across here. So that's between 1 and 2 milliseconds. That's a nice spark line. It looks good, nice and steady. We have some coil oscillations. We have our firing line. Everything in here looks nice and stable. Now let's pull down our current waveform, or amperage. We saw in the last section what our saturated looks like. So now let's see what our current limited looks like. So here's our current limiting waveform. See it there in green. Started just about 0 amps. We had some oscillations. Now, where the last waveform made this nice arc and started to kind of level off the top, this one rises really rapidly and then flattens right out. Has a pretty sharp transition here. Flattens out till we turn it off. So we're going to draw a line where our current limiting starts in relative to our waveform here. And you'll notice that right as the current limiting starts, that is right where our waveform flattens out on our current side. And we're just given enough voltage differential to maintain that level of charge. Then we have our firing line when the circuit turns off, nice spark line. We have some coil oscillations in here, so we have some power left over. So this is a good example of a current limited waveform, both in the primary voltage and in what you would see in the amperage. The scope capture that we have here is secondary ignition. In the primary video, I put secondary pickups around both the ignition coil wire and the number 1 spark plug wire. And this is the pattern we get from that. Up here in green, that was the image from the number 1 cylinder, the number 1 spark plug wire. I only was using that as a sync or synchronization signal. So down here in red, that is what we got off of the ignition coil wire. So this is all 8 cylinders. So we can view on one screen across the screen all 8 cylinders and see what each cylinder looks like as it fires to look for any issues related to that cylinder or its secondary ignition components. We sync to the number 1 cylinder and then we write out the firing order so that between number 1 cylinder and the next time the number 1 cylinder fires, we know that this was cylinder 1. The next one in firing order on that particular engine was cylinder 3. Then cylinder 7, 2, 6, 5, 4, 8. And in this manner, if we find that we have a problem with one of the cylinders, or if we had a misfire and we weren't sure which cylinder, and we were on our ignition pattern and we noticed a very easy to spot problem, we could use this method and go straight to the cylinder we're having an issue with. And this is also just a really good example of a secondary waveform.
Okay, hopefully after all that, you got a good feel for what our primary current is going to look like, and now we've also put the two together. So you should have gotten a good picture of how electrically the coil is using its current and voltage as it goes through the circuit. And we've seen some good ones, and we've seen some not so good ones. And once again, when we finally make it out to the shop for class, make sure you refer back to this because you probably won't remember all this by then. But that's okay, that's why we have these. And that means that we get to see you in the next video.